In this video, we're going to look at equilibrium and in particular calculating the equilibrium constant Kc. So before we get into what the equilibrium constant is, let's just talk about what we mean by dynamic equilibrium. It's a really important definition that we need to know. So we're talking about reversible reactions. For example, hydrogen and iodine reacting to form hydrogen iodide. So if I start with hydrogen and iodine in a container and react them together, then they will react at a particular rate. And that rate will depend on the concentration of hydrogen and iodine. So what will happen is that will slow down. As the reaction goes on, we use up the hydrogen and iodine. So the rate of the forward reaction decreases as the reaction goes on. But then we have this reverse reaction, which is going from hydrogen iodide to hydrogen iodine. So when hydrogen iodide is made, it is able to decompose and break back down. And what will happen is they will keep reacting forwards and backwards. And eventually we will reach a point at which the rate of the forward reaction, because the forward reaction is slowing down and the reverse increases, at equilibrium, the rate of the forward and reverse reactions are equal. So this is our most important explanation or definition for what we call dynamic equilibrium. So we've got the word dynamic, meaning that the reaction has not actually stopped. The reaction is just continuing in both directions simultaneously at the same rate. And that's just because the conditions have lined up to the point where the concentrations of those three particles has reached a point where it affects the rate so that they're all equal. Now, what it doesn't mean is the concentrations are not the same, but they don't change after that point. So as fast as hydrogen and iodine are turning into hydrogen iodide, the reverse reaction is happening at the same rate. It means that there would be no overall change in temperature, because I wouldn't expect to see any energy change because the forward reaction and the backwards reaction would have opposite and equal delta H values. I would see no change in the colour. Even though I have a coloured reactant, iodine, it's being made and broken down exactly the same rate. I'd just basically see nothing. It would look like the reaction's stopped, but it hasn't. It's just stopped changing because of those rates being equal. It also means that we can approach the equilibrium from either direction. Okay, so I didn't need to start on the left-hand side. I could start with hydrogen iodide and I'd still reach exactly the same concentrations under the same conditions of temperature and pressure. We can therefore describe equilibria. Okay, so when we describe them, the concentrations of the reactants and products, although they don't change, they're not equal. So there isn't the same amount of hydrogen iodide as there is H2 and I2. And how much there is on each side depends on the pressure and the temperature and anything else that affects reaction rates. So we can talk about equilibrium position as being either on the left or the left-hand side, and you can use these shorthands when you're explaining things, or more on the right-hand side. And generally, if we wanted to talk about yield or something like that, we talk about the right-hand side, because that's the thing we're trying to make often when we talk about equilibria, where we're trying to make a product. You can talk about reactants and products. Left-hand side and right-hand side is generally a little bit better because they're all reactants at the end of the day. And of course, if we change the temperature, concentration or pressure, we will move the position of equilibrium. But that's not the focus of this video, because the focus of this video is to look at the calculations. So let's look at a sort of made up reversible reaction where the capital letters refer to the reactants and products. So we've got A and B are my left-hand side or reactants. And we've got B and C on my right hand side, or we can call them products. And then these little numbers in front are just the moles of each. So the balancing numbers, stoichiometry, whatever you want to call them, really. So we have a constant value that describes the relationship between the concentrations of C and D compared to B and A. So the equilibrium constant is given the symbol Kc, and it is basically a ratio. So K in chemistry stands for constant. The reason that we don't use C for constant is because C stands for the speed of light, which is like the universal constant. And then the C actually stands for concentration, and that's because there are many other types of equilibrium constant. And in this topic, we also see Kp, and in later topics, you'll see Ka and Kw as well. So big K, capital K, means equilibrium constant. If you've done the rates topic, you will also know there's another lowercase k, which stands for rate constant. So there's a lot of K's in this part of chemistry. Be careful that you know which one you're talking about. And then in the expression, our square brackets here mean concentration. So that would be the concentration of D, concentration of C, concentration of A, concentration of B, and that is because this is the equilibrium constant using concentration. And then the small letters up here, that's our, things that we're doing to the power of. So everything is raised to the power of the number of moles in the balanced equation. Okay, so if we know how to write an expression for Kc, which is actually often worth marks, so don't skimp on making sure. Most common things people do is sort of miss out the square brackets, for example, so make sure that we do that correctly. That means that in theory, some Kc calculations can be very much just as easy as putting those numbers into the expression. So let's put that into a Kc calculation, and this is just a relatively simple one. So we're given a balanced equation, which is important because we need these numbers, which is 2 and 4 and 1. And we also need the concentrations. And what we've actually been given is not concentrations, we've been given the volume and the number of moles of each substance. Okay, so all I need to do is do moles over decimeter cubed to get my concentration, which is always in moles per decimeter cubed. So 0.04 divided by 0.2 is 0.2. 0.84 divided by 0.2 is going to be 4.2, and 0.32 divided by 0.2 is 1.6. And Kc is concentration of NO2 to the power 4 times the concentration of O2 all over the concentration of N2O5 squared. And I'm going to put my numbers in, so just make sure that we get them all the right way round, because they could be in any order. So I've got 4.2 to the power of 4 times 1.6 on the top. And then at the bottom, I've got 0.2 to the power 2. Now, I highly recommend, we don't need the brackets, I just put those in for clarity because my numbers aren't that clear sometimes. And that's very helpful if you're not very good at distinguishing between your bigger and smaller numbers. For the calculator, make sure that you're using your fraction button, the one with the little squares above each other. Also make sure you know where to find the x to the power button, because you may have to go further than x squared or x cubed, as in this example. Just be really, really careful that you don't end up, because it's very easy to put something on the wrong, like half of this fraction, if you don't pay attention to what's going on the top and what's going on the bottom. So I put all of this in, and because they've got large numbers at the top and a small number squared at the bottom, it's actually going to be 12446.784. I put all the numbers in. That's not an appropriate number of significant figures because that's 8. So I would probably put it to 3 for this example. It's not the best example because some of my answers have only been given to 1 because it's not an exam question. So I just go 12400. Okay, now what about the units? So the units for Kc is what we're going to look at next. So Kc only involves moles per dm cubed on the top and on the bottom. So basically the units for Kc are just going to be derived from moles per decimeter cubed. Now, that means every single one of these concentrations is in moles per decimeter cubed. How many moles per decimeter cubed have I multiplied together on the top? Well, I've got 4 there and I've got 1 there. Don't forget that there is a 1. So if I add those together, like if I had x to the power 4 and I times it by x, that would give me x to the power 5. If I then divide that, at the bottom I've got moles per decimeter cubed, and this time it's squared. Okay, so little reminder, when you do a power to a power, so if I take x cubed and I square it, then I actually multiply them together because that's like x cubed times x cubed, right? So that would give me x to the power 6, 3 times 2. If it's a minus number, I still do the same thing, I multiply it. Okay, so at the moment I have moles per decimeter cubed to the power 5. So I take each part of that, moles to the power 1, 1 times 5. So at the top I've got moles power 5. dm to the minus 3 times by 5 is minus 15. Looking all a bit ridiculous. And then underneath I've got moles to the power 1. 1 times 2 is 2, so that's moles squared. dm to the power minus 3. Minus 3 times 2 is minus 6. Okay, then what do I do to simplify it down? Well, when you divide, you take away because these are powers. Okay, so again, a similar situation. X cubed over x is x squared, or x to the power 7 over x to the power 3 is x to the power 4. And of course, we can get minus numbers too. So moles to the power 5 over moles to the power 2 is moles to the power 3. I've really not given enough space here, have I? And then minus 15 minus minus 6 gives me dm to the minus 9. So I'm going to do a few more examples of that. So if you're happy with finding units, you can just move on to the other calculations. But all we actually really need to do is, because what we know is it's going to be Kc is going to be the right hand side over the left hand side. It's going to be moles per decimeter cubed to the power 2 over moles, in this case, per decimeter cubed to the power 3. So actually, all I'm going to do here is I'm going to do 2 take away 3 is minus 1. So 2 there, 3 there, 2 take away 3 is minus 1. So overall, it's going to be moles per decimeter cubed to the power minus 1. Moles 1 times minus 1, also minus 1. Minus 3 times minus 1 is plus 3. Okay, let's look at that with another example. So all I did was the right hand side moles over the total left hand side moles. So in this situation, I've got 4 moles on the right hand side, 2 moles on the left hand side. 4 minus 2 is minus 2. So it's to the power minus 2. So I end up with moles minus 2, 1 times minus 2, minus 3 times minus 2 is minus 6, dm6. One thing I want you to notice also is that this relationship is always times minus 3. So that relationship stays. One of them is positive, the other one will be negative, and vice versa, because they will always vary by a factor of minus 3 because they are linked together. You can't separate them. Last one looks ridiculous, but if we use this method, it's going to be a lot easier. So on the right hand side, I've got 10 moles in total, 4 of NO2, 6 of H2O. On the left hand side, I've got 11 moles in total, 4 and 7. So I'll just do 10 minus 11 is minus 1. So the units will be moles to the minus 1, dm to the 3. It's actually exactly the same as that one up there, just because there's 1 more mole on the left than there is compared to the right. Okay, now we're going to look at calculating Kc using what we call ICE tables. So here's an example. It's a nice easy one to start with. We have been given a balanced equation at the top. We're going to need that, of course, for the Kc, but we're also going to need it for something else. 2 moles of SO2 left to react with 1 mole of O2. So in this particular one, that matches these numbers. There is no reason that it has to match those numbers. And then we have let them react. So that's the initial moles. That's what the I in ICE stands for, initial. And then we've allowed equilibrium to get to a point of equilibrium. There's a volume been given, and we've been given the number of moles of just a single thing afterwards. And we're going to use that to work out the moles of everything else. So ICE stands for initial moles, change in moles, and then the equilibrium moles. And then I've added another bit on the end, which is the concentration. Okay, because don't forget that Kc the C stands for concentration. So we put in the initial moles. There is 2.00, 1.00, and we haven't added any of that, so I'll put 0. And then we put in the equilibrium moles that we've been given. So we've been given oxygen is now 0.92. So I'm going to find the difference between 1 and 0.92, and that's 0.08. That's my change. Change needs to have a plus or minus sign. So O2 has gone down, which it would have to, of course, because it can't possibly go up because there wasn't any SO3. So it's gone down by 0.08. So the ratio of oxygen to SO2 is 1 to 2. So every time I use 1 mole of oxygen, I use 2 moles of sulfur dioxide. And so if I have used up 0.08 moles of oxygen, it means that I will have used up 0.16 moles of SO2. And so the new value for SO2 is now going to be 1.84 moles. And on the other side, the amount of moles of SO3 I'm going to make will be the same as the moles of SO2 used up. So I'm going to increase by 0.16, and therefore I would have 0.16 as my moles at equilibrium. These are moles. Kc involves using concentration. The volume is 2 decimeter cubed, so I take each of these values and divide by 2 to get the concentration in moles per decimeter cubed. And that's going to be 0.08. Then write out my expression for Kc. This is really worthwhile. If you didn't have told to do it in the question, do it anyway. Because otherwise what you're going to do is you're going to forget about the squared, because everybody's used the 2 already in the table, and then we forget to use it again in the equilibrium constant expression. Also be really careful about doing this the right way around. It's really easy to do it upside down. And make sure we get the right value. So SO3 is 0.08 squared over 0.92 squared times 0.46. Small value 0.0164. Units, 2 on the top, 3 on the bottom. 2 take away 3 is -1. Moles to the power -1 decimeter cubed. Okay, now let's look at a slightly different one. So this time I've been given a volume again, fine, and I've been given initial moles, and this time I have been given initial moles. I'm just going to fix my O2 there because it's annoying me. There, boom, there. I've been given the initial moles of 3 different things. Okay, so this time I actually have an equilibrium mixture that contains all of the substances, both the left-hand side and the right-hand side. There's no rule to say that we have to start on either side, or that we start with 0 of one side. So I'm going to put those numbers in the right place. Those are my initial moles. And then it says after heating we get a new equilibrium position. So it already was at equilibrium, and then we heated it, and we're getting a new value 0.88 of NO2. So I'm going to put that there. And then it says determine Kc, explain whether the forward reaction is exo or endothermic. We'll do that once we've got the Kc value. Okay, so what we've done is we need to work out how that's changed. So it could have changed in either direction. As it happens, the moles of NO2 has increased, and it has increased by 0.64. So I put a plus on that side. And then we can use the same technique to work out what's happened to the rest of them. So oxygen is on the same side as NO2. That means oxygen will increase, okay, because they're on the same side. So if one goes up, the other must have gone up too. It's gone up to 0.64 for NO2, but the ratio is 4:1. So I divide 0.64 by 4, and I get 0.16. So my new number of moles of oxygen is now 0.22. On the other side of the equation, N2O5 must have gone down because that's how I made the NO2 and the O2 increase. It's going to go down by half of 0.64 because of my ratio of 4:2. So I'm going to take away 0.32 moles, and my new value is going to be 0.52. So really get to grips with this step. Do not skip it. Make sure you're clear whether it's plus or minus and why it is the values it is based on the balanced equation. Okay, and then the last step is simply dividing by the volume. Just need to be careful because the volume is in centimeter cubed, so that's 0.3 decimeter cubed. Just do 300 over 1,000. Now I'm going to divide each of these by 0.3 to get my concentration, and it ends up being 1.733, 2.933. I don't want to round too much at this point. They're all recurring decimals. They're all like recurring threes. Don't round too much until you're sort of getting to the end. And my Kc, let's do the expression, is going to be NO2 to the power 4, O2, and a concentration of N2O5 to the power 2. Putting everything in, 1.73. Nope, see, it's so easy to do. Try again. 2.933. You see what mistake I did there? It's really, really common, is to take something from the wrong side of the table. And that is squared. Putting all that in, and my Kc ends up basically being 18 to 2 significant figures, and 2 significant figures is fine. The units, I've got 5 moles, 2 moles, 5 minus 2 is 3. So the units are going to be mole to the power 3, and then we do minus 3, that 3 times minus 3 is minus 9. Now let's look at whether the forward reaction is exo or endothermic. So I increase the temperature because it says after heating. And we just need to know which direction did the equilibrium shift. So I increased temperature and the moles on the right hand side increased. So that means it shifted to the right hand side, or to the products if you prefer. So if it shifted in that direction when I heated it, now that means that when you heat an equilibrium, that will favour the endothermic direction. And since it moved to the right hand side, that tells me that the right hand side, or the forward reaction, is endothermic, because when I heated it, the number of moles of NO2 and O2 increased. The Kc value also increased. So I could have calculated the original value of Kc, because I do have the initial moles, and you could calculate concentration and put those in, and what you will see is that will be a smaller value of Kc because there's less moles of NO2 and O2 compared to N2O5. So Kc increased, the reaction shifted to the right hand side, and that means that the forward reaction must have been endothermic. Okay, what about if instead of giving number of moles, we're told about the percentage change? So here's an example where that happens. And it tells us that 1 mole of CO was reacted with 1 mole of hydrogen. So notice that's not the same ratio as the balanced equation, which is absolutely fine. You can have as many moles as you like to reach equilibrium. It really doesn't matter. There's 0 moles of methanol. They've been reacted. There's a volume which I'll use when I get to concentration. And now instead of saying how many moles of any one of these substances is present at equilibrium, instead it says that 15% of the carbon monoxide reacted. So we're going to decrease by 15%, and 15% of 1 is 0.15. So that is now 0.85. Now we mustn't now rush this and try to put 0.85 for hydrogen. It's not the same number of moles in the equation. So if the carbon monoxide went down by 0.15, now we just use this value, don't use percentages now. Now use this actual number of moles to work out everything else. So this one is going to go down by 0.3, and this is going to go up by 0.15. So don't skip this change in moles. That's where all the things go wrong. The other things that go wrong is the Kc the wrong way around and the forgetting about concentration. So that is now going to be 0.7 and that is going to be 0.15. Divide everything by 5 decimeter cubed and we get 0.17, 0.14 and 0.03. Put that into Kc. Don't forget about squaring your hydrogen and you will get a value of 9.00 and the units are moles to the power minus 2 dm to the 6, and that's because we have one thing on the right, we have 3, so 1 take away 3 is minus 2, that's where my minus 2 comes from, and then I just times minus 2 by minus 3 to get the dm. Okay, last example is one where a slightly trickier one, and it's trickier for a couple of reasons. So the first reason is because it's what we call a heterogeneous equilibrium. And heterogeneous means that not everything is in the same physical state. We have solid, aqueous and aqueous. So normally for Kc we would either have everything in an aqueous state, because aqueous means dissolved in water, which means it has a concentration. Or we'd have, like in the previous ones we've been doing, we'd have gases. Now gases, we can measure either the pressure or we can measure their concentration, because there are a particular number of moles of gas in a particular number of dm cubed. So we can measure moles per dm cubed for gases. What we can't do is measure a value for moles per dm cubed as a solid. Solids do not have a concentration. The other way to look at this is that saturated solution. So saturated means that as much lead chloride can dissolve. What that means that at that temperature, if that's what Kc equals and the solution is saturated, if I add more of this PbCl2 solid, no more will dissolve, because that's what saturated means. It means it cannot dissolve anymore under those conditions. Only thing I could do is change the temperature, which could shift the position of equilibrium and change this value of Kc. So Kc is fixed. This doesn't affect it. And so solids are not included in equilibrium constants. So the Kc for this is in fact Pb2 plus times by the concentration of Cl minus, and it's squared because there's a 2:1 ratio. And there is no PbCl2 in my Kc expression because the concentration of solids can't change or have any effect on the position of this equilibrium. There's a clue anyway in this question, so if you look at the units, that the units are moles cubed dm to the minus 9, which means there are 3 mole per dm cubed units and no other units there. So we're not dividing this by anything else. Okay, but that's all we've got is one value. We've got this 2.0 times 10 to the minus 5. We know what Kc equals, but we've got technically 2 unknown values, Pb2 plus and Cl minus. We don't know what the concentration of either of them is. Now, if I make a solution of lead 2 chloride, then what I do is I take that solid and I dissolve it. And when it splits up, as we can see from the equation, every 1 mole of this makes 1 mole of that and 2 moles of Cl minus. So that means if that's all I've done is dissolve that, Pb2 plus, if we say that the concentration of Pb2 plus is equal to X, because we don't know what it is, then the concentration of Cl minus is equal to 2X, because the only place those chloride ions came from is from that equilibrium where there's a 1:2 ratio. Okay, so now I can put that into my Kc expression. What I've got is, there's my Kc value, 2 times 10 to the minus 5. The concentration of lead ions is X, and then I'm going to times that by the concentration of chloride, which is 2X, but I'm also going to square it. So you might be really fast with your maths. If you're not fast with your maths, my biggest tip for you is to do everything step by step and don't just go trying to rearrange this all at once. You don't get any extra marks for that. So if I take 2x and square it, that's going to be 2 squared as well as x squared. So that's going to equal 4x squared, right? That's 2x times 2x. Then I'm going to times that by x as well. And so what I'm going to end up with is 4x cubed. And that's still there, 2 to the minus times 10 to the minus 5. Again, step by step. Don't try and cube root it until you've divided by 4 first. Okay, so divide both sides by 4. And so I'm going to get 5 times 10 to the minus 6 on this side equals x cubed. And then I'm just going to do a cube root of 5 times 10 to the minus 6. Make sure you're using your times 10 to the power button, or that you're using brackets so that you're cube rooting the whole thing and not just cube rooting 5 and then timesing it by 10 to the minus 6. And then x is equal to 0.017 moles per dm cubed. And that is my concentration of lead. If I wanted the concentration of Cl minus, I'd take that value and times it by 2. But in this question, we only wanted the concentration of Pb2+.